Hello everyone, my name is Ziheng Lu. I'm a senior researcher at Microsoft Research. I'm really glad to use this chance to share some of the things happening in our lab and introduce to you a fellowship program that is open to application now. Here's the title of today's talk, Materials Research from the Perspective of Computing. I try to cover some of the most important aspects here, of course, from our perspective, including data, models, and downstream applications. Here's the outline of this talk. First, I'll briefly give some background information on material science, and then I'll try to introduce some of the computational tools that is often used. After that, I'll try to give you some of our thoughts on the challenges from the perspective of computation. Of course, you can say they are challenges, but at the same time, they are also opportunities if you take a different angle, right? So I also try to introduce some of our efforts in this area, how we try to tackle materials problems by developing data-driven and machine learning methods. I also try to cover 3 projects, namely the Graphormer, a transformer-based foundation machine learning model for atomic structure representation, LOSIKO, a data-driven atomic structure optimizer for unlabeled data, and this molar. I don't really know how to pronounce this, but basically it's a graph-based model for molecular generation. So here we go. Material science. What is it, and why do we, Microsoft, care so much about it? So if you look back into human history, you'll find that probably the entire human civilization is actually pushed by the discovery and development of new materials. Say, if you look back into ancient times, we have those Stone Age, the Bronze Age, the Iron Age. All of them are named after the representative materials our ancestors started to use, right? So 100 years ago, we started to be able to use steel, and this led us into this information age, not really information age, but industrial era. And now we're in this information age. If you think about it, this entire empire of internet, cell phones, computers are built upon semiconductor materials, basically highly pure silicon. It's not unfair to say that these tech giants like Microsoft wouldn't be possible without silicon, without material science, right? So in fact, materials are so important, we rely so much on them in our daily life, so much so that we cannot really feel them. So after looking at these old materials, let's look at something new, the stuff material scientists are looking at every day now. So on the left-hand side is this metallic alloy that is used in aircrafts. So these alloys need to be very strong under very harsh conditions, like very, very high temperatures. So like 180,000 degrees high, while still remaining 150 megapascal modulus. In the middle, this is organic perovskite material for solar cells. For this material, we want it to absorb light as much as possible and to convert the energy from the photon to electrons with efficiency as high as possible. So below is the numbers that is required for this material to be commercialized, to be really useful. So on the right-hand side is the lithium transition metal oxides. So these materials are used in batteries as electrodes to store energy. So for these materials, we want them to hold as many as lithium ions as possible, and want the lithium ions to move in them as fast as possible. So a good cathode material has these properties listed here. So you can see that these materials are drastically different. However, if you look at how I described them just here, I found very clear property targets to them. So these targets are the properties that they have to bear so as to be used in real life. So here comes the goal of materials research we care about. That is target-specific material design. So we have those numbers we require, and we need the material with those numbers. Basically, that's it. So basically, we want to discover or develop a new material as quick as possible once we are given the properties we care about. So before we look at how this target is approached by computation, let's see how conventionally it has been done. A very typical material synthesis process goes like this. So in a lab, we chose some precursors, starting materials, and then we weigh them. Then we mix them. In order to mix them well, we use a boiler to grind them together. Then we put the mixed materials in crucible. We put the crucible in a furnace. And then we heat the mixture of material at very high temperature, like 1000 degrees high. Then we keep our fingers crossed and hope that these precursors will just react to form something we want, something has a property we want it to have. So how do we know if the synthesized materials has all the properties we want? A short answer is by trial and error. A less short answer is we use some of the prior knowledge from chemistry to guide us through the design of the experiment. Nevertheless, it's very much like doing alchemy, or in Chinese, 炼丹, right? It's funny, right? So actually, this is what I've been doing during half of my graduate years. It's painful. The other half is, of course, computation. However, don't get me wrong here. This approach is very important and might not be that efficient as you might think. So if you check my publication list, you will find that I have quite a lot of them, meaning that at least this method worked for me. In fact, historically, this trial and error approach led to almost all the important discoveries in material science before. So you may ask, then why we are ditching it while we are not using it? This is because despite its effectiveness, this approach is just too slow and too expensive. We need something much faster, something with higher rate of success, and something that can go beyond our limited design space. So here comes the computation. Let me first quote Dirac on this. The underlying physics laws, written as mathematical equations for chemistry, is already known. What Dirac is talking about is actually the Schrödinger's equation for electrons. So basically, by solving it, we can calculate the energies of any systems, any sets of atoms in any configurations. This formulates what we call a potential energy surface. So the potential energy surface, or PES, is a function that describes the mapping between atoms, atomic positions, and the energy. If one knows the PES of a chemical system, basically, in principle, all the properties can be computed. So how does one compute the PES? In principle, we should use quantum mechanics. So unfortunately, quantum mechanics is just too expensive for practical systems. In fact, if we are only treating electrons as quantum, which is also known as Bohr-Oppenheimer approximation, the exact solution of quantum mechanics can only be solved for a couple of atoms, like under 20. So how many atoms are there in a real chemical system? Say a bottle of water is on the order of 10 to the 23 level, so which is way beyond what we can deal with Schrödinger's equation, right? So, however, something cool happened last century. These two guys named Cohen and Pope developed an approximation called density function theory, or DFT, saying that instead of solving for wave functions, we can actually deal with electron densities. So this tremendously lowered the computational cost. Nowadays, using DFT, we can roughly, routinely solve for systems with thousands of atoms. If we combine that with periodic boundary conditions, we can actually simulate a lot of things, including this bulk water. So what is DFT? It's a bit hard to explain it in a very short amount of time, but actually, we have some people working here at Microsoft trying to speed it up. But for now, we can just treat it like a black box, which is what most computational material scientists do. This black box takes in the atomic positions and spit out an energy, as well as a bunch of electronic properties such as band gaps. In addition, we also get the gradient of energy, which is the forces, and the second order gradients, which is relevant to modulus. Using the forces, we can solve for the the Newton's equation for the acceleration. Once we have that, we can simulate the movement atoms. That is pretty much molecular dynamics. So here's a picture I always liked. So with many years of effort from computational chemists, we can now use DFT as a computational toolbox. We don't really need to know much about it. We should know, but we don't have to know. So with this toolbox, we can screen over all these materials we know by computing their properties using DFT. So this is extremely cool. In fact, many computational databases have been built today. However, there's some catch to that. So I'll mention later. One of the most important issues is that with screening, we are confined to this predefined space. So we are pretty much can only do on this data set. We cannot reach out for whatever is beyond. So this is where data-driven computing or AI or machine learning methods come in. The machine learning is known to be able to extract high-level features from large data sets. From the latent space of those features, it is possible to drive the discovery of new materials, even with desired properties, right? So here are some pictures showing where AI has achieved great success in recent years, say image recognition, speech, self-driving cars, games. So can we use ML, machine learning, to drive materials discovery, materials research? So despite the great success of machine learning in many fields, the application of it in material science is actually suffering from several issues. Here you can see I listed a few. First is data, which is the biggest hurdle from my perspective. I'll mention this in a second. The second one is the models. There's plenty of machine learning models now. For deep learning, there are also many different architectures. The success of them all depend on one thing: the representation of material in a computer. Basically, you can't really just give the computer the XYZ coordinate of molecule or material and expect it to work well on those inference or whatever tasks. This is because such a representation is not symmetry invariant. So what does that mean? So when you do rotation, translation, or mirror operations or permutations on a material, this material does not actually change. There's still this piece of material, but the computer could not recognize it. It could recognize it as a different piece of material if you're doing these operations. So the other hurdle is the inverse design model issues. Nowadays, it's still very hard to get these generative models to work well like those on images. So all these led to difficulties in downstream errors. Let's quote a thing that is usually quoted in this field: no single catalyst was discovered by pure computation over the 40 years, which is also true to machine learning. So we have to make this work. So, enabling AI or machine learning for material science is one of the top priorities here at Microsoft Research. And we've just started a strong investment in this, in all these three aspects: data, computational methods, and downstream applications. I introduced some of our work in this area in a few minutes. So before we go into the detailed work, I wanted to talk a bit more on this data issue. Here I show the minimal sizes of data sets where machine learning, especially deep learning, has achieved quite some success. The number usually goes up to 10 million. It's quite a large number. So now let's take a look at what we have in material science. So on the left-hand side, we have the computational database, say Materials Project. It has millions of entries of DFT computed crystal structures. Such a number is not really that bad. However, I want you to notice one thing. That is, the properties from these entries are not very accurate. Actually, for complex properties like the catalytic properties of these solids, they can hardly be calculated, and therefore it is pretty much missing. So what about experimental results? They are the gold standards, right? Unfortunately, for specific tasks, there are not too many of them. More importantly, these data can hardly be trusted. On the right-hand side, I show this ionic conductivity of solid electrolytes from exactly the same recipe, but are synthesized and tested in different labs. You can see that the values are quite different. They span quite diversely, over an order of magnitude diverse. So with these problems in mind, we did some preliminary research at MSR, Microsoft Research. So the first piece of work I would like to introduce is LOSIKO, Local Similarity Kernel Optimization. As previously mentioned, we have quite a lot of computational data. However, their labels are not that accurate and sometimes just missing. This method is created to utilize these data to obtain atomic structures of molecules, materials, and complex systems driven by data. So as you can see from the name, local similarity kernel optimization, this method matches the local environments of atoms in structures of interest to a database. When we're computing the similarity, we convert the XYZ coordinates of a local environment to a vector, which we also can call it embedding for machine learning people. This embedding is invariant to rotation, translation, permutation, and all these mirror operations. So the conversion can be done using predefined functions based on physics, like slope. It can also be extracted using machine learning models as latent vectors. I'll introduce one of the models in a second. After we extract the embeddings of the local environments, we can drive the structure to maximize the similarity between the local structures to the database. Finally, we get an optimized molecule or a piece of material. That is what we want. So there are several features to this method. First, we only need the structure data. So the data does not need to be labeled. Second, the method is very fast. It actually scales linearly with the number of atoms. Third, we have a good database. If we have a good database, this method can actually achieve quite high accuracy. Finally, this method can be used for biased material research, or you can say it's inverse material design to some degree. This is done by curating different databases. After all, this method is data-driven. Whatever you feed into the model, whatever results you would get. So here are some benchmark results. We optimized the QM9 datasets using the method and got an RMSD of 0.08 angstrom, which is pretty good. This value is actually smaller than the number between different quantum chemical methods. So somehow we can say that we reach the quantum chemical, a very good standard. So we also tested this method on complex systems. Obtaining structures of these complex systems has been very difficult because the bond topology is ill-defined. This makes this conventional force field not working. One example we show here is a proton defect in this lithium cobalt oxide. So this material is a cathode material in lithium-ion batteries. You can see that using this, actually for this work, we used stable box structures from materials project as database, and using that, we can actually recover the hydroxyl group perfectly as DFT2 using LOSIKO, but that only takes several seconds. For DFT, it should have taken like minutes to hours. Similarly, we also carried out a LOSIKO optimization of this semiconductive interface. As you can see, the top atoms at the interface are driven to the positions where the bonding environments are much more reasonable compared with its initial configuration. So finally, let's try to play around with the database a bit more and see if we can bias the optimization for inverse design. Here we use the carbon as an example. we specifically constructed 3 data sets for this task. First, the first one contains diamond, the second one contains graphite, and the third one contains a bunch of different carbon polymorphs beyond graphite and diamond. Of course, these two are already contained in this third one. Then we generated the random carbon structures and relaxed them using these 3 databases respectively. As you can see here, the 3 databases give drastically different carbon materials with different densities and different band gaps. And all of these properties are somehow close to their mother materials in the database. Say for this graphite-like structures here have the density close to graphite and the band gap close to 0. Therefore, LOSIKO really has some capability of doing inverse material design. Now let's go into the second piece of work I would like to introduce to you, which is Graphormer. You may have heard about this work. It has made some noise in the area of machine learning and molecular modeling in this community. As mentioned before, there's a significant shortage of high quality data. In this meantime, we actually have quite large data sets that are kind of crappy. The properties are not that accurate. So one way to solve this data scarcity issue is to use the pre-train and the fine-tune method, which is often used in this NLP, the natural language processing projects. So Graphormer is essentially a model that extracts high-level representation of atomic structures. If you think about it, the structures of molecules are usually represented as graphs, which is quite natural. The nodes are the atoms, the edges are the bonds. Therefore, the graph neural nets have been widely used to model molecules. However, graph neural networks, or GNNs, are limited. They have this over-smoothing problem. We cannot really make GNN models really very large and with too many layers, because then all the node vectors will be similar after training. It also has some problem in expressiveness I will show you later. So Graphormer is a totally different game. Actually, the idea is pretty simple and neat. It's just a very standard transformer, but with 3 key encodings added to capture the structural features of the graph. So there's this spatial encoding, which captures spatial relations between different nodes. There's also this centrality encoding, which captures the importance of nodes or the edges in the graph. And finally, we have this edge encoding, which incorporates the edge features via a bias term to the attention module in the transformer. So Graphormer pretty much is just a standard transformer with this spatial encoding, the centrality encoding, and the edge encoding. With this architecture, we can actually show that mainstream GNNs are special cases of Graphormer, which is quite impressive. Therefore, it should have better expressiveness in all of them. In fact, Graphormer can pass the first order WL test, while GNNs cannot, most of the GNNs. One example is shown here. GNNs cannot distinguish these 2 graphs or molecules, while Graphormers can. After testing, we also find that Graphormer really does not have this over-smoothing issue of GNNs, which I have just mentioned. So with these features, Graphormer has performed really well in a number of tasks. We actually won the first place in the KD-DTI Cup last year and the OC220 contest on this prediction of a catalyst by Meta. So recently, we've been benchmarking the model to see if it can really do this pre-training and fine-tuning task, and the result is actually very promising. You can see that the model actually has a very good potential to resolve the data scarcity issue in material science, at least to some degrees. So now that we have developed these foundation models, we also wanted to try to directly generate new materials or new molecules using generative models. This is the third task we want to do, the very challenging task. And here's a piece of work done by Microsoft Research Cambridge, which is not on the Beijing side, not in Asia, but in Cambridge. Microsoft Research is a very large organization. So in this work, our research in the UK made something called Molar. Bear with me if I'm pronouncing it wrong. So this generative model has a standard encoder and decoder modules, which is quite standard. What makes this different is that it uses structural motif as a vocabulary. During the decoding process, motifs are picked and are connected by the picked bonds. And this architecture actually allows us to generate molecules with scaffolds as initial seeds. So here are some benchmark results. It really performed quite well. And especially when we want to when we want the scaffold to be maintained during the generation, which is somewhat the task that is quite realistic, and the score is pretty amazing for this task. So those are pretty much what I wanted to share today. In the end, I want to introduce to you our fellowship program. This program is quite well known in the computer science community. Now we are doing this AI for science, and we also wanted to identify the best young scholars in the area of material science in different computational area. For material science, it should be especially we want to give focus on computational material science, but other areas of material science are also welcome. The aim of this fellowship is to discover the rising stars of computational science or natural science, broadly speaking, in Asia-Pacific region. We also want to use this to empower our outstanding PhD students to do better research and inherit the research genes of Microsoft Research Fellows. So if you're good or anyone around you is good, don't hesitate to apply for it. From my knowledge, in the area of computer science, if you get this fellowship, you pretty much get a ticket to whatever company or university one wants to get into. Also, there's money involved. I think it's tens of thousands of US dollars for the price. I'm not sure about it. Please check the website to see if I'm correct. So finally, thank you all for the attention.